So last time we took a look at the same gas at different temperatures. Now we're going to take a look at different gases at the same temperature, right? So before, same gas, different temperatures. Here, different gas, same temperature. So for example, if we think about xenon and helium at the same temperature, kind of what does that mean, right? Well, if they're at the same temperature, they have the same average kinetic energy. However, if we think about kinetic energy, it's more than just the speed of the molecule. That is an important factor, but it's also the mass, right? So if you want the equation, kinetic energy is equal to 1/2 the mass times the velocity squared. So you can see not only does the speed play a factor, but the mass plays a factor as well. And that makes sense, right? A baseball going 100 miles an hour has much less kinetic energy than a car at 100 miles per hour, right? The more mass you have, the slower speed you have to be going to have the same kinetic energy as something that has less mass. So if we take a look at this plot again, and this time we kind of thought about two gases at the same temperature. Again, we're going to put count here, speed right here. What we would notice is that the more heavy gas kind of looks colder, has that same kind of bigger lump, less spread out, and then the hotter gas ends up looking like it's going faster because it is going faster. But again, they have the same kinetic energy because they're at the same temperature. They just have different average velocities because the lighter gas has to be going faster in order to have the same kinetic energy as the heavier gas. So when you're given kind of plots like this, be able to identify, which one's the heavy gas, which one's the light gas, which one's at low temperature, which one's at high temperature, that kind of thing. We won't go into it too much, but again, if you do go into physical chemistry, this is a very important concept.